Okay, so we've had several lectures about the symmetric group and conjugation in the symmetric group and centralizers in the symmetric group. And now I want to tell you about a very special subgroup that the symmetric group has, which is called the alternating group. So we have Sn, the symmetric group on n letters, and in there we have An. This is the alternating group. And it's an index 2 subgroup, so Sn, An, this index is 2, which means that the cardinality of An is n factorial divided by 2. And so what is this group? How do we define it? So to define it, we have to do one more thing first with permutations. So let's define the alternating group An. Okay, so first we need to observe that every sigma in Sn is a product of transpositions. So recall a transposition is just a 2-cycle. Okay? Transposes two numbers I and j. Okay, so why is this true that every permutation is a transposition? Well, we know that every permutation is a product of disjoint cycles, in fact, in a unique way. So to see this claim, it's sufficient to see it for a cycle. Now, if I have a case cycle, so assume sigma is a case cycle, then sigma is conjugate to our favorite case cycle 1, 2, up to k, because we know that any two case cycles are conjugate. We saw how to do that explicitly. Okay? So now, if I write 1, 2, up to k, this case cycle is a product of transpositions. And then I conjugate this case cycle to sigma. Then, as we've discussed before, this means this is the same thing as conjugating the transpositions that appear in the decomposition of this case cycle and then multiplying them together. Now, if I conjugate a transposition, I get again a transposition. So if I know how to write this particular case cycle as a product of transpositions, then by conjugation, I'm able to write any case cycle as a product of transpositions. And by cycle decomposition, I'm able to write any permutation as a product of transpositions. Now, so now for this case cycle 1, 2, up to k, I can write it explicitly as a product of transpositions. So I tend to, there's a natural thing to try, which is the transpositions 1, 2, 2, 3, and so on up to k minus 1k. And then I tend to have a hard time remembering if we should put 1, 2 at the right or at the left. So let's put it in one direction and then see if this works or not. So let's do 1, 2, 2, 3, and so on. And at the leftmost, we will have k minus 1k. Let's see if this is correct. So here I should start multiplying from the right. I have 1 goes to 2, 2 goes to 3, 3 goes to 4, and so on, and k minus 1 goes to k. So this is not correct. Okay, so let's try it the other way. 1, 2, 2, 3, k minus 1k. Does it work this way? Well, let's try now. So if I have to compute this product, well, then 1 is fixed in all these permutations, except this one that's most at the left, that in composition we do last. And then it sends 1 to 2. So that's the same as what's going on at the left-hand side. And then 2 is fixed up to this point. It maps to 3. And then 3 doesn't appear anywhere to the left. So this way we convince ourselves that this one is correct. And then what I told you in words now about getting sigma. So if sigma is equal to tau 1, 2 up to k tau inverse, then then sigma is equal to tau 1, 2 tau inverse tau 2, 3 tau inverse dot 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 tau k minus 1 k tau inverse, and each of these tau transposition tau inverse, these are transpositions, and in fact we know exactly what they are. Remember that tau 1, 2 tau inverse, this is none other than the transposition tau of 1, tau of 2. Apply the thing by which you're conjugating inside. And just be careful about the order, that you have to do tau, blah, tau inverse, and not tau inverse, blah, tau. But you can always do some small example, like with a 2-cycle and a 3-cycle, to make sure that you haven't messed up the order, sort of like what I did here, that this one is wrong, this one is correct. OK, so this way we get a general k-cycle, and then by cycle decomposition we get a general element. So every sigma in Sn is a product of transpositions. Now, we can try to make the following definition. An is the set of sigma in Sn such that sigma is a product of an even number of transpositions. Okay, so I said we can try to make this definition, but what is the problem with this definition? Well, a priori, we might be worried, it's a perfectly valid worry, that the same sigma might at the same time be a product of, say, 2 transpositions and 3 transpositions. Because here we gave a way to write a general permutation as a product of transpositions, but it's easy to see that there is more than one way every permutation can be represented as a product of transpositions in many ways. This is just a convenient one. And then you might be worried, maybe my permutation sigma is a product of 7 and 14 transpositions, or 7 and 10 transpositions. Oops, 7 is odd, 10 is even, then this definition doesn't make sense. Okay, but in fact, so caution, need to show the number of transpositions well, that representing a sigma in Sn cannot be both even and odd. Okay? Now, one way to tackle this problem is to change perspective a bit and use things that we know from linear algebra. So, idea to get around this problem, and there are different ways. So, one idea to get around this problem. There is a natural embedding of the symmetric group into the general linear group. For any field F. So remember, we talked about this one in one of the first lectures. This is the group of n by n invertible matrices over the field F. How do we how do we do this embedding? We define let EI be a, so this will be I going from 1 to n, be a basis of f to the n. So it's the standard basis, if you want, of coordinate vectors. And then I define sigma of EI to be E sigma of I. So I'm permuting the basis vectors. And now remember that to give an invertible linear transformation, this is the same thing as sending a basis to a basis. Now here I'm clearly sending a basis to a basis. As a set, I'm sending the basis to itself. But the order of the basis elements is changing. So the matrix associated, so this gives, let's maybe call this A sub sigma. So, okay, so A sub sigma is in GLNF, and this is the matrix whose ith column is E sigma of I. So these will be matrices that in every column there is exactly 1, 1, and the rest are zeros. In every row there is exactly 1, 1, and the rest are zeros. And the entry in which you have a 1, there are no two columns in which it's the same, and there are no two rows in which it's the same. Okay, and so this map from Sn to GLNF, it is just the map which takes sigma to the matrix A sigma. And so this is a homomorphism, and it's injective. And now what we can do is we can define an in a different way. We can define this by the aid of this embedding into GLNF as the set of sigma in Sn, such that when we have a matrix, what can we do to it? We can take its determinant. So we can require that the determinant of the matrix A sigma is equal to 1. Now, remark, there aren't many possibilities for the determinant of A sigma. By what I defined these matrices A sigma to be, their columns are the standard basis vectors, just not in the same order. Now, you know that if you just change two columns in a matrix, then if you transpose two columns of a matrix, what that does to the determinant is it multiplies it by -1. So the determinant of A sigma is always either plus or -1 for all sigma in Sn. And by what I just told you about that to compute the determinant, it's the number you can start from the identity matrix and swap columns two at a time. You know that that's multiplying the determinant by -1. So the determinant of A sigma is equal to 1 if and only if sigma is a product of an even number of transpositions. Because if I write sigma as a product of transpositions in any way, that's telling me exactly which columns to swap to go from the identity matrix to my matrix A sigma. So if I, for example, if I write sigma as a product of an odd number of transpositions, that means I make an odd number of swaps of the column and I get to A sigma. But then by what we know in linear algebra, the determinant is a product of -1 an odd number of times. So it's -1. If sigma is a product of an even number of transpositions, I make an even number of swaps. But we know the determinant is well defined. Okay. If you have seen a definition of the determinant, you might have seen a definition that has used already these notions of even and odd, but one can also define the determinant more abstractly without making use of this notion of the parity of the number of transpositions appearing. So this is okay. And then we say, so I have already used the words, we say sigma Sn in Sn is even if, well, if it's the product of an even number of transpositions, or equivalently, the determinant of A sigma is equal to 1, and we say that it's odd if it's the product of an odd number of transpositions. Equivalently, the determinant of A sigma is -1. And sometimes we also, for this reason, we also write sine of sigma is equal to 1 if sigma even, and sine of sigma equal to -1 if sigma is odd. All right, and so we have a map. Sn goes by sine to plus or -1. And sine is a homomorphism. Why is that? Well, we could mess around multiplying, transpositions, but another way to see that is, again, to appeal to linear algebra and say that this is because the determinant of AB is the determinant of A times the determinant of B. If you think about what's going on here, this map, it is just the composition of the homomorphism Sn into GLNF followed by the determinant. Now, of course, the determinant goes to F cross, but we said that if something is in the image of this embedding, then its determinant is in plus or -1. And then all we are saying is that the composition of two homomorphisms is a homomorphism. And the definition of AN here as being the things with determinant 1, that is the even things, is saying by definition that the kernel of this sign map is equal to AN, the alternating group, and so in particular AN is normal in Sn. Another way to know that AN is normal in Sn is, well, this map is surjective. So whatever the, well, I mean, AN is by this point, it's really the kernel of this map, but also AN is a subgroup of index 2. Every subgroup of index 2 is normal. Okay, so let's finish the discussion of alternating groups for now by giving some examples of the concepts that I just introduced. Specifically, I just want to tell you how even and odd works in computing inside the alternating groups. Then we will come back and look at the example of the group A5 in detail later. So, okay, so one thing is about the caution. Let's quickly, remember we had this issue of permutation, making sure that it's not a product of an even number and an odd number in a different way of transpositions at the same time. Let me just show you an example of how a transposition can be a product of one transposition and 3 transpositions at the same time. So to do that, let's take our favorite transposition, 1, 2. And now let's conjugate it by another transposition, 2, 3. Okay? Now we know how to do this, right? We know how to do this very well by now. We apply 2, 3 inside to the 1, 2. So we get 1, well, that's not affected, and then the 2 is mapped by 2, 3 to 3. So we get 1, 3. But now let's think about just what's going on here. So this, let's call this sigma. So sigma is a product of 3 transpositions by left and 1 transposition by right. Of course, this product is not disjoint, but when we said that every permutation is a product of transpositions, this is no longer a disjoint game. They're not required to be disjoint. Okay. But 1 and 3, while different, have the same parity, so we're okay. This is not a contradiction to what I said before. Now, the other thing I want to tell you about even and odd is that it's very easy to compute when you have a permutation and you have its cycle decomposition to compute whether it's even or odd. So let's go back to our case cycle 1, 2 up to k, written as 1, 2, 2, 3 up to k minus 1k. How many transpositions are there here? 1, 2, k minus 1. So what this is telling us is a case cycle. It's telling us the following confusing thing, that a case cycle is even if and only if k is odd. Okay, and so if and only if means that a case cycle is odd because there are only 2 choices, if and only if k is even. So a 4 cycle is odd. 4 is even, a 4 cycle is odd. Now, to compute the sign or the parity of a more general permutation that need not be a case cycle, you just use the following rules. So even times even is even, odd times odd is even, and even times odd is odd times even is odd. So this is for for parity of permutations. This is not for multiplying integers, obviously. But the reason that we have this is just because of this sign homomorphism. And so if I'm saying that odd times odd is even, what this means in terms of the sign homomorphism is that I have -1, that's the sign corresponding to odd, times -1, that's the sign corresponding to odd, is 1. And then this one is, for example, and when 1 corresponds to even. This one, even times odd, this is 1 times -1 equals -1 times 1 equals -1. Okay.